Hi again to everybody. So let's continue with our lesson on the methods of proof. For today, we will be looking at the third type of proof. But before we proceed with the third type, let's just have a quick review of what we have finished so far. So we have finished two methods already. We have our direct proof, and in this method, what do we have? We are given P implies Q. And what's the process? We assume P to be true, and then we supply supporting evidences for P to arrive at Q to be true so that we can conclude that P implies Q is also true. So it's a very straightforward method. And in the last lecture video that I have sent you, I have discussed proof by contrapositive. And for the proof by contrapositive, we are still given P implies Q, but from the method itself, we must get first the contrapositive of the given, and the contrapositive of P implies Q is not Q, implies not P. And what will we do here? We now assume that not Q is true, and then using again some evidences to back up our statement of not Q, we must be able to show that not P is also true. And if we have shown that not Q implies not, if we have shown that not P is true, if given not Q is true, then in that we have already shown that not Q implies not P is also true. Of course, our final conclusion there is that P implies Q is also true. So for today, we will now be looking at the third method. And the third method is what we call proof by contradiction. Okay, proof by contradiction. And for this third type, still we are considering P implies Q. And what will we now do with the given P implies Q? So same thing will happen. We now assume P to be true, okay? But this time, we will consider not Q will also be true. So that will be the assumption. P is true and not Q is equal to true. Then, from this assumption, since we are using both P and not Q as our assumptions, we can work around with these two propositions so that we come up with a contradiction somewhere along our argument. So along our proof, we must be able to arrive at a contradiction. So from the title or from the name of the third method by contradiction, we need to find a contradiction so that when we now find a contradiction, then we will have the final conclusion that this must be true. Again, for the method of contradiction, we are given P implies Q. We will assume P is true. Then we will also assume that not Q is true. We work around with these two propositions so that we come up with a contradiction Finally, we conclude that P implies Q is also true. Let's discuss an example for this. First example, we have if A squared is even, then A is also even. Okay, so this is our P and this is our Q. If P, then Q. So according to the process, we assume that P is true. Okay, sorry. We assume P is true. Okay, and then we also will consider not Q to be true. And what is not Q? If A squared is even, then A is even. Q, A is even. Therefore, for not Q, A is not even. Or in other words, if A is not even, then A is odd. Okay? So that will be our assumption. Our assumptions will now be A squared is even. Okay, that's one assumption. Second assumption, A is odd. Okay, so where do we begin with our proof? So let's now start with uh, the proof. And we can use the fact that A is odd. Let's use the line A is odd. Okay, so using A is not even or A is odd, this means that A can be represented as 2 multiplied by another integer plus 1. Isn't it? We have done this before. So here B is an integer, any integer. So that is now the value of our A because A is assumed to be odd. So if A is 2B plus 1, then if we want now to consider A squared will be 2B plus 1 raised to 2. Why? Since A is 2B plus 1, then A squared is 2B plus 1, the quantity squared. Using our algebra, this will now be 4B squared, square of the first term, plus twice the product of the two terms. 2B plus 1 is 2B times 1 is 2B times 2 will be 4B, plus the square of the second term, 1 squared is 1. And then looking at the resulting expression here, for the first two terms, we can factor out 2, which will now give us 2 multiplied by 2b squared plus 2b plus 1. This is the value of a squared. And since we have already expressed a squared as 2 times 2b squared plus 2b plus 1, then what can we say? This is also an integer because b is an integer. 2 times an integer plus 1. So, what can we say here? Hence, a squared is odd. Okay? So, from this line, it means a squared is odd. But, what is our assumption? Our assumption is that a squared is even. So, because of this line here, we can now see a contradiction. So, where is the contradiction? Assumption, a squared is even. What we have obtained here is a squared is odd. So in some books, you will find this symbol here, this symbol, like a symbol for lightning. That symbol means contradiction. So, since we have obtained a contradiction here in this line, then we can now conclude that if a squared is even, then a is also even. Okay, there you go. So how do we do again proof by contradiction? Given P implies Q, we assume P is true. We get not Q, assume that to be true. Use these two propositions as our basis in the proof. Work around with these propositions, with these assumptions, until you arrive at a contradiction. And if you have a contradiction on hand, you can now conclude that the original statement implies Q is true. Let's have a second example. Second example here is the square root of 2 is irrational. Okay, square root of 2 is irrational. Okay, so we can rewrite this, or we can restate this, that if we are given the square root of 2, then it is irrational. Okay, so square root of 2 will be our P, and it being irrational is our Q. Assume P to be true. Consider your not Q. Okay, so if your Q is irrational, we get its opposite, then the opposite of rational, or irrational I mean, is irrational. So we will now consider this to be true as well. Okay, therefore, combining the two, we are now saying that our assumption will be square root of 2 is irrational. Okay, square root of 2 is rational. Okay, if square root of 2 is rational, then square root of 2 must be expressed as a over b. What's a rational number again? A rational number, from the term itself, ratio, is a number that can be expressed as a fraction of two two integers. Okay, of two integers. Of course, the denominator must not be equal to 0, and uh, and a and b must be relatively prime with each other, meaning the greatest common divisor of a and b is equal to 1. Okay, so when we say that a fraction is a rational number, then the greatest number that can divide both must be equal to 1. Okay, so an example is 1/2. 1/2 is a rational number because uh, the greatest common divisor of 1 and 2 is equal to 1. The greatest number that can divide both 1 and 2 is equal to 1. But if you have 3 over 9, 3 over 9 is not rational because both the numerator and denominator can be divided by 3. So in that case, the greatest common divisor will be 3, which violates the definition of uh, the rational number. Okay, so let's go back to this part here. We are now considering the square root of 2 is equal to AB. Square root of 2 is assumed to be rational. Therefore, it can be expressed as a over b. A and b are integers. B must not be equal to 0. The greatest common divisor of a and b must be equal to 1. Now, what can we do with this? So we have square root of 2 equals a over b. Let's square both sides of the equation so that we can get rid of the radical sign there. So that now gives us 2 is equal to a squared over b squared. What else can we do here? We can cross multiply b squared. That gives us 2b squared is equal to a squared. So if a squared is equal to 2b squared, then it means that a squared must be even, right? Because a squared is expressed as 2 times b squared. Therefore, a squared is even. And if a squared is even, then a must be even also. How do we know that? From example number 1. If a squared is even, then a is also even. So where can we use that? A is even. So if a is even, then a can be expressed as 2 times another integer. Let's use another integer. Let's say c. Okay. So c is again an integer because a is even. Therefore, a can be expressed as 2 times c. C is an integer. So where can we use that? So let's go back here. We have a squared is equal to 2b squared. So we have 2b squared is equal to a squared, but a is 2c, so that must be 2c squared. So we just substituted the value of a, giving us 2b squared equals 4c squared. Divide both sides by 2, we get b squared is 2 times c squared. Okay, 2 times c squared. So what do we have here again? B squared is 2 times c squared. Therefore, okay, thus we can say that b squared is also even. And if b squared is even, then b is also even. Okay, if b squared is even, then b is also even. Okay, again, this is coming from what we have done in example number 1. Okay, so far, what do we have? What do we know? A is even, B is even. Therefore, if B is even, we can rewrite B as B equals 2D, where D is again an integer. Why? Because B is even. Okay, and where did we find A and B earlier? Isn't it that we have A and B from our original assumption? Okay, so going back to that part, we have the square root of 2, therefore, is equal to A over B, but A is 2C and B is 2D. And if A is 2C and B is 2D, then we can divide both sides by 2. Okay, And what happened there? Because of that part, where we have canceled out 2 and 2. Since A is even, B is even, A is 2 times C, B is 2 times D, what's the implication of this? What's the implication of this line here? The implication of this line here is that the greatest common divisor of A and B is equal to 2. Okay? Because you have seen that A is even, B is even, therefore A is 2 times C, B is 2 times D, giving us the greatest common divisor of A and B is equal to 2. But where is the contradiction? The contradiction now comes in here, that the greatest common divisor of A and B is equal to 2. Why? From the assumption that we have given here, if the square root of 2 is rational, then the square root of 2 is A over B, where A and B are integers, B not equal to 0, and that the greatest common divisor of A and B is equal to 1. But what we have obtained here is that the greatest common divisor of A and B is equal to 2. So we now find here the contradiction. Okay? Therefore, final conclusion, therefore, the square root of 2 is irrational. That will now be our final conclusion. Okay? So that's where the contradiction kicks in. Next example. Third example. Prove that in a room of 13 people, 2 or more people have their birthdays in the same month. So how can we restate this? If there are 13 people in a room, then 2 or more people will have their birthdays in the same month. Okay? So P will be assumed to be true, but we need to consider not Q. So what is our Q? 2 or more people have their birthdays in the same month. So what will be not Q? No 2 or more people will have their birthdays in the same month. So that's our not Q. And we will assume that not Q is true. That's the rule for the proof by contradiction. And we want to arrive at a contradiction somewhere along the line of our proof. And where can we find the contradiction? So let's analyze again. There are 13 people in the room. That is assumed to be true. Then the second assumption is that no 2 or more people will have their birthdays in the same month. Okay, so logically, if no 2 or more people will have their birthdays in the same month and there are 13 people, then what can we say? Then there must be okay, so prove that 13 people, if there are 13 people, 2 or more people have the same birthdays in their 2 or more people have their birthdays in the same month. So our assumptions are 1, there are 13 people. 2, no 2 or more people will have their birthdays in the same month. Okay, so what can we now see there, if both are true, 13 people and no two people must have their birthdays in the same month, then there must be 13 months in a year. O, di ba? Parang gagawin natin is we distribute them one person per month para walang madodoble. But since 13 people are involved, so kailangan mo 13 months to be able to distribute them per month. But the reality is we only have 12 months. So there you will find your contradiction. Since you need to have 13 months in 1 year to be able to distribute the 13 people na ang magba-birthday lang per month, isa. Okay? But that's not the reality because we only have 12 months. Therefore, we now conclude that if P, then Q. Okay? So I did not write down the entire statement because it's quite long. So we can now conclude that if P, then next example. Example number 4. And example number 4, we have, suppose A is an integer if A squared minus 2A plus 7 is even, then A is odd. So this must be our P, and this must be our Q. P is assumed to be true. We need not Q. What will be our not Q? A is not odd or A is even. So those will be our assumptions. One, assumption, given A squared minus 2A plus 7 and A is even. So where do we begin? Again, we have the assumption is A is even. So if A is even, then it means A is equal to 2B, where B is an integer. So we've been using that definition very often. So A is even, so A can be expressed as 2 times an integer. So B is an integer. And what can we do with this? We can substitute it in the other assumption. So we have A squared minus 2A plus 7 is the same now as A is 2B. Okay, A is 2B. We're just substituting A in the expression. And this now gives us 4B squared minus 4B plus 7. What's the assumption for P? That A squared minus 2A plus 7 is even. So we want to show that this is even, but for the first two terms, we can factor out, okay, actually for the three terms, we can factor out 2. So this now gives us 2 times 2B squared minus 2B. Okay, sorry. That's 2B squared minus 2B for the first two terms only. Para mas madali lang makita muna. Okay? Plus 7. But if you like to express that, 7 is the same as 6 plus 1. So 7 is 6 plus 1. So why am I doing that? So if that's 6 plus 1, we can now factor out 2 from this expression here and from 6. So giving us 2 multiplied by 2b squared minus 2b plus 3 and then plus 1. So I exaggerated that because we can now see here the contradiction. Where's the contradiction? So we have already expressed a squared minus 2a plus 7 as 2 times 2b squared minus 2b plus 3 will be an integer because b is an integer plus 1. So what's the indication there? It means because of our expression, we now have a squared minus 2a must be odd. Because of this, you have 2 times an integer plus 1, the expression of a squared minus 2a plus 7. But our assumption is that a squared minus 2a plus 7 is even. Therefore, we now find here a contradiction. Since there is a contradiction there, then we now conclude that if, okay, so we now conclude that suppose a is an integer, if a squared, okay, if a squared minus 2a, so if a squared minus 2a plus 7 is even, then a is odd. So that will now be our final conclusion. Of course, a is an integer. So there you go. That's the third type of method of proof that we will be using, proof by contradiction. Just a quick recap for the proof by contradiction. What is happening here for the proof by contradiction? Quick review. We are given the statement P implies Q. We assume P to be true and we consider not Q to be true as well. So use now your P and not Q as your assumptions. Work around with those assumptions until you encounter a contradiction. So if you now have a contradiction somewhere along the lines of your proof, then you now conclude that P implies Q is also true. So there you have it for today. We have the method of proof. So till our next lecture, God bless you all. See you once again.